Today I talked about energy and where we've come from in energy and how we've used it and where we need to go in the future. And if you look at how we have built our modern society with regards to energy, the way that we've come to where we are today is by lighting materials on fire. That's basically what the Industrial Revolution has given us, and it's how all of our modern era runs. We take these fossil fuels that we dig out of the ground, and by lighting them on fire, we release energy from them. And if you want, you can think about these fossil fuels as having been pushed up a hill, an energy hill. So it's like a ball. You put a ball up a hill, and it's got potential energy, and if you let it go, it gives you that energy back. And fossil fuels are basically like balls being pushed up a hill, but instead it's chemistry that was pushed up a hill. And so what you had was all this sort of carbonaceous material that is in plants and animals, algae, that got buried underground, and under just the right conditions, pressure and temperature, nature, over tens of millions of years, changed the bonds and pushed the chemistry up and up these hills to give us things like methane and propane and oil. And what we do is by lighting that on fire, those bonds break and the energy comes out and the chemistry rolls down the hill. Now, the challenge with that is that all of these chemistries that have been made for us by nature are finite. We're going to have to build the future on another way to pump energy up and down hills. And it turns out that unlike the IT revolution, which is based on processing the same material, silicon, the energy revolution will depend on developing new materials. And it's already happening. New materials are what are going to make the difference in so many clean tech energy conversion and storage technologies. And so what we do at MIT is we work on the development of new materials that efficiently and cost-effectively push electrons up hills and then let them roll back down when you need them. So if you think about, so I'll give you a couple of examples. In the area of solar energy, well, the sunlight is your pump, right? And the current material that we use to pump electrons up hills is silicon. But silicon is not actually the optimal material for solar cells because it's not very good at absorbing light. So what we do is we say, well, what else could we use as the pump? And it turns out that carbon is a very good absorber of light. And so we make solar cells out of carbon, and because it's so much better at absorbing light, you can make it 1,000 times thinner. And because you can make it 1,000 times thinner, you can make it ultralight, you can make it on any substrate, not just glass. You can weave it into fabrics, and you can make it even transparent, and it will still produce electricity. Now, why can we do this? Why can we now make solar cells with all of these new carbon-based materials instead of silicon? The reason is that we happen to live in a completely new age of materials design. So, I love how we can call the age we live in by the material that's important to that age, but I also love that we'll never be able to do that again. And the reason is that now, today, we can literally make any material you dream up. And so we can put atoms exactly where we want in a molecule or a solid and make anything. And so that has enabled us to rethink solar cells and to rethink energy technologies more broadly, and to be able to make these ultra-light, ultra-efficient, and ultra-cheap solar cells made out of carbon. All of my research is on the supply side of energy, but it's really important to also, when you talk about energy, to think about the demand side. And I'll give you an example. LEDs have really revolutionized the energy consumption of light. So lights are now 1,000 times more efficient than they were in the 1700s. But at the same time, we use 40,000 times as much light as we did in the 1700s. So the way in which we use energy is an extremely important part of the problem, and we have to work on that as well. Now, with regards to innovation, where we are with designing new materials to change the game in energy and water is at the very beginning. And what's needed more than ever is new ideas and innovation that takes advantage of atomic scale materials design and applies it to these challenges. One of the things I worry about is that if we take existing technology like silicon for solar cells as an example, and we race that to the bottom, what you do is you may create a fairly inexpensive energy technology, but you put all of the innovators out of business. And the question is that the right one? And I believe the answer is no. And so we have to continue investing on the innovation side in this sector so that in 10, 20, 30 years, we have this sort of revolution that we're going to need.